Hello, welcome to For Us Learn. In this video, you can try a 1-mark question to do with motion in an electric field. Once you've had a go, we'll discuss the solution so you can check your answer. Let's take a look at the question. A proton, starting from rest, takes time t to move a distance d in a uniform electric field. See left diagram. The voltage across the charged plates is V. How long would it take, in terms of t, for an alpha particle starting from rest to move a distance d over 2 in the uniform electric field shown in the diagram on the right? Assume the mass of a proton is the same as that of a neutron. So you can see in this diagram on the left here, this is for the initial scenario of a proton moving in an electric field. And the diagram on the right here is for the second scenario of an alpha particle moving in its electric field. Notice that the distance between the charged plates here is half as big as the distance d on the left here. And also the voltage across the plates on this right scenario here is twice as big. It's 2V compared to V over on the left here. Please pause the video and have a go at this yourself. It's really important you do this to get the most out of this video. When you're done, unpause the video and we'll discuss the solution. Okay, welcome back. Let's first figure out how the time taken by the proton depends on the variables in the problem. Once we've worked that out, we can see what the effect of changing these variables will be on the time for the alpha particle. A key bit of info in the question is that both particles move in a uniform electric field. Now, hopefully you'll know that for a uniform electric field, the electric field strength E is given by the voltage V between 2 points divided by the distance separating those points, D. Now, a uniform field means that the proton will experience a constant electrostatic force to the left here as it moves, and will therefore undergo a constant acceleration. From Newton's second law, we know that the acceleration that the proton will experience will equal the resultant force acting on the proton divided by the mass of the proton. And the resultant force here is simply the electrostatic force acting on the proton, which is equal to the charge of the proton, Q, multiplied by the electric field strength, E. Let's replace E here with the expression above, V over D. So we get that the acceleration of the proton is given by Q times the voltage V divided by m, the mass of the proton, times the separation or distance d. Now, given that the proton undergoes constant acceleration, that means that the Suvat equations are at our disposal, and in particular the equation S equals ut plus half at squared looks promising, because u, the initial velocity, is 0. S, well, that's just d, so let's just replace s with d here. Half at squared. And if we rearrange for t here, we get that t is equal to 2d divided by a rooted. And now we can pop into here, we can replace a with the expression we just found up here. So if we do that, we find that the time for the proton to move all the way over to the left plate is given by 2m d squared over qv, all square rooted. Let me just point out that we could have replaced q with the charge of the proton, E, but you'll see later that this is not really necessary. So what we found here, as promised, is an expression for the time of travel for the proton and how it depends on the variables in the problem, namely the mass, the distance between the plates, the charge, and the voltage across the plates. So we've really done the bulk of the hard work. What we need to consider now is how the variables change for the alpha particle You'll recall that an alpha particle consists of 2 protons and 2 neutrons. And since the question tells us to assume that the mass of a proton is the same as that of a neutron, we can say that the mass of an alpha particle, call it m prime or dash, is simply equal to 4 times the mass of a proton, which we've just been calling m so far over here. And similarly, since an alpha particle consists of 2 protons which are charged with charge E, and neutrons are electrically neutral, that means the charge of the alpha particle, call it q prime or dash, is simply equal to twice the charge of a proton, which we've been calling q over here. And we're also told in the question that the voltage across the charged plates that the alpha particle moves between is 2V. So we can call that voltage here, V prime, 2V, and the distance that the alpha particle moves, call it d prime, is equal to d, the original distance, divided by 2. So now to figure out the time that it takes the alpha particle to move all the way over to the left here, call it t prime, we just need to use this formula here that we figured out. This formula that tells us how the time depends on the variables in this problem. So t prime is just going to be given by 2 times the mass of the alpha particle, m prime, times the distance it travels, d prime squared, divided by the charge of the alpha particle, q prime, times the voltage that it travels across, v prime, all square rooted. Now let's just replace these variables with what we know over here from this list here. So let's replace m prime with 4m. D prime we can replace with d over 2 and then square it. Divided by q prime, which is 2q, multiplied by v prime, which is 2v, and then we have to square root all of this. Now hopefully you can see here that when you square d over 2, you're going to get a factor of 1/4, which is going to cancel the 4 here. So on the top here of the fraction inside the square root, we're just going to end up with 2m d squared. On the bottom here, we're going to end up with 4qv. All square rooted, of course. And the final step here is to say, okay, if we compare this with our expression here for the original time, and remember the question is asking for the time for the alpha particle to travel in terms of this original time t, we just notice here that the only difference between this and this is that there's an extra factor of 1 over square root of 4 here, multiplied by the original expression for the time. And of course 1 over square root of 4, that's just a half. Okay, square root of 4 is 2, and so what we found here is that the time for the alpha particle is just the original time, so all of this is just t from here, the original time, divided by 2, and we're done. If you found this question tricky, I recommend you try it again as many times as you need to in the future, until you can answer it comfortably by yourself. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and leave a comment. I'd love to know how you found this question. Thank you for listening, and I hope to see you soon.